Okay, good morning. I'm going to go through part 3 of this run-through. For those of you studying IGCSE Edexcel, this is the paper from January 2023. So let me write that in for you. So they haven't written the year because they weren't sure if they were going to use this paper or not when they prepared it. I don't know why. During COVID, they didn't put the year on it in case they cancelled the exam. So this is a January 2023 paper. I went through 2 parts already. So we're halfway through the paper. This is the 1P paper, so it's for combined science, double award, as well as the paper 1 for physics, if you're doing the full physics IGCSE. Okay, so these run-throughs, you can go through them at your own pace, and I often say that you can listen to them at double speed, because when I'm talking, I need to talk clearly, but when you're listening, you can actually take the information in at a faster rate. So it would be worthwhile increasing the speed and then stopping the video when you want to copy down a solution. Okay, so for those of you preparing for your IGCSE this summer, I've put some 2023 papers in already from the November sitting and from the June sitting, I think. So the 2023 papers are already there, and I've got the January 23 paper here, and I've also got the paper for 1PR, because this is 1P. There's also a 1PR version. If you want me to do the January 1PR as well as this one, then I can do that. So just leave a comment somewhere under this video, and if I get enough views and enough likes and it's popular, then I'll do more GCSE videos. But originally I set this YouTube channel up for people doing A-level, and the A-level gets a bigger audience than the GCSE. So it's really up to GCSE students to show that these videos are of use to them, because obviously you can probably, all the older papers, you can just find the mark schemes online and use them, which is what one of my students said, that going through the videos was not something she wanted to do. She just wanted to see the answers. So you can just get the mark scheme if that's what you want. Okay, so let's see, we did this question. This was in video 1 where it was on motion. So we're now going to question 6. And question 6 is about the waves topic. So maybe I'll do question 6 and I'm going to see question 9 because they're both on waves. So this question is about refraction and total internal reflection, which was a special request from one of my students. So I actually did a live session, I'm talking about face-to-face, recently, and I had a number of students turning up during the holiday. Okay, so this question is mainly to do with how optical fibers work. Now, so to do that, we need to understand refraction and we need to understand total internal reflection. So optical fibers are used, for example, in the internet, and they use light waves for communications. That's how the internet works. How you're watching this video, the signal goes through fiber optic cables and by use of light waves. And light waves travel very fast, even in the fibers. The fibers slow them down a bit to about 2 times 10 to the 8 meters per second, and it's much faster than sending the signal using the old-fashioned method, which was with electricity. So you've got to tell us, you've got to tell the exam which of these statements is correct about waves in general. Okay, I put a cross where there is a problem. Waves transfer energy and transfer energy, information, and matter. Well, matter is not transferred. The waves just oscillates, vibrates through the matter. And then here it says waves do not transfer energy. Well, you know immediately that waves are a form of radiation transfer. Okay, so from topic 4, energy transfer can happen by radiation of light or sound. As I'm speaking, your speaker on your device is radiating sound waves to your ears. So anything that spreads out as an oscillation is a form of energy transfer. And then C says waves transfer energy, that's correct. And then it says without transferring information. Well, that's not true. Sometimes they do transfer information. So the answer must be D, and you'll see why. Waves transfer energy and information without transferring the matter itself. So the matter is something through which they travel. The matter itself stays undisturbed once the energy has traveled through it. It will go back to its normal position. So that's how you get the 1 mark. So the answer is D. Okay? Okay, carrying on. Any array of light passes from glass into air. Yeah, so a ray of light means a very narrow beam of light, a ray, from air into a glass optical fiber. So this is a blow up of the glass fiber. Okay, this is the entry point through air into the glass. Diagram 1 shows the path the ray of light after it has passed through the boundary. So the boundary is here. Let's do the boundary in blue. Okay, so the boundary is here. So the boundary is the blue side. So once it passes through, they want you now to draw the path of the ray of light in the air before it passes through the boundary. So they want you to draw it in the air. Okay? So this side of the boundary is what they want you to draw. Now, whenever you want to draw a ray diagram, you have to draw what's called the normal. Normal is always drawn at right angles to the boundary. So I've drawn this normal in and I've labeled it. And you can see the ray of light is then traveling at an angle to the normal inside the fiber. Okay, so this is the fiber. Okay, an enlarged version of it so you can see what's happening. And you got to work out, well, which way was the ray of light traveling, yeah, before it went into the glass. So what you need to know for this question, and I put this here, in the refracted ray always bends towards the normal. In the denser material, which in this case is the glass. So if it's going into the denser material, the ray of light will bend towards the normal. That means before it got into the glass, it must have had a bigger angle to the normal. Okay? So if it had a bigger angle to the normal, yeah, so it would be, I'm going to try and draw it straight. It would be like that. And I've drawn it in black. So the ray going in, this angle would be the angle of incidence. So you can see I actually put a ruler on my screen to try and draw it straight, but the screen is upright, so it slipped at the end. But you should use a ruler in the exam to make sure that you have got it as clear as possible for the examiner. Okay? So, sorry if I made some crackling noise, I was trying to get rid of the ruler. So the angle in the air, here, the angle in the air will be bigger than the angle in the glass. Alright, so that's basically what they want you to see that you've got, and all of that is understanding how the 1 mark comes from this knowledge. Okay, so that's when you're watching these videos, you're actually learning and you're revising the topic again. Whereas if you just look at the mark scheme, yeah, you might be able to find out if your answer was right or wrong, but you will not be doing the full revision. Okay, so this is exam technique. The next part of the question says, state the name of this wave behavior. Yeah, the one that we just explained. The wave behavior responsible for the path of the ray of light as it passes from air into the optical fiber, as it passes from one material into the other. Well, the answer is, it's known as refraction. Okay, so once you know what refraction means, and I just explained it to you, you can then understand how fiber optics works. Okay, so the ray bends when it goes from the air into the refracted, into the glass. They call it the core. So here's the mark scheme. So I'm slowing down so you can have a look at the wording in the mark scheme. So we've now understood this process by which the light bends if it comes in at an angle, yeah, is an important part of this topic. And it also means that it slows down. So if it bends towards the normal, it also means it slows down, okay? Now you could also draw wave fronts on the wave, and that's something you should revise if you haven't revised wave fronts, okay? So sometimes in these questions, you need to draw wave fronts, and wave fronts are drawn perpendicular to the ray. So that's something I showed when I did it in the live session. Okay, there's part C. So part C is going to go into total internal reflection. So part C goes into total internal reflection. So the next part of the question is what's happening inside the core once the light is kind of trapped inside it. Okay, and for that you need to understand the critical angle. Okay, so here they've then continued where the ray of light came in. The ray of light entered there, and that's the bit of the question that we've already answered. And then you can see it's traveling in, and the fiber optics cable is bending around, yeah? And you can see that I've drawn another normal here to show the first point where the ray of light hits the surface, internal surface of the core of the cable, of the fiber optic cable, okay? So it says, the diagram 2 shows the path of the ray of light as it travels through the optical fiber. And this is called fiber optics. So over here, you'll also notice that I've drawn the normal again. There is the normal. And I've drawn it here. And I've drawn it there. Because the normal is essential for you to be able to understand the concept called the critical angle. Okay, so to be able to answer these questions, you need to understand that the critical angle is the key to understanding these. So if the angle inside the glass, so theta 1 over here, if theta 1 is greater than the critical angle, which for glass is about 42 degrees, if the angle of incidence inside the fiber optic is greater than the critical angle, yeah, so in other words, the angle of incidence inside is greater than the critical angle, then total internal reflection will occur, yeah, whenever the theta to the normal, the angle to the normal, is greater than C. And you can see the angles are quite big, theta 1, theta 2, and theta C. When that happens, you get the light internally reflecting totally. None of the light can get through the boundary where I've drawn the yellow circle. Okay, and none of the light can come out here. It gets totally internally reflected. So the angle here will be equal to theta 2. And the angle here will be equal to theta 3. And likewise over here will be equal to theta 1. Okay? Hope that makes sense. So wherever the light is incident on the boundary, it will be totally internally reflected. And that it says explain the path. To explain the path, that's what they want you to do. You've got to say it's because the light is in the denser material. It's optically denser. That means its refractive index is greater than air. Okay? Remember, it came in from the air and then it travels through the denser optical fiber, and you've got to mention refractive index and stuff like this. Now, I haven't put all the words in, I've spoken them, so you've got to listen, pause the video, and then go and look at the mark scheme, and hopefully then you'll understand what you need for this kind of question. And this is a very common question in IGCSE. Okay, hope that helps. So the answer was on the mark scheme part C. So this is part C that you need to look at. Okay, and that's for 3 marks and the wording that they're expecting. Okay, all right, remember when you're doing these papers, you can't expect every practice paper to be explained to you on a one-to-one basis. So having these videos is the next best thing where you can actually understand the topics and have a look at the way the teacher is explaining it, in this case me, so you can get a full understanding of the concepts in these questions. So here's another question on waves. So we're going to go straight into question 9. So this one again is on waves. So we just did the refraction and total internal reflection. Now we're going to look at more basic aspects of waves. So it says question 9 is about waves, and the diagram represents a wave. Okay, they want you to determine the amplitude, and they want you to measure it with a ruler. So amplitude means the maximum displacement of the oscillation or the wave, and they want you to determine the wavelength of the wave by measuring it with a ruler. Okay? Now, if this was a graph, they should really have explained that there's 2 axes. So up and down would be displacement. Yeah? How much is it displaced? So this up and down, the vertical, would be displacement. And that's usually measured in meters. Yeah? Could be centimeters. In this case, they want you to do it in centimeters. But they want you to determine the amplitude. Well, the amplitude is the maximum displacement. From where? Okay, well, the 0 displacement is the dotted line. So the 0 displacement, yeah, is the point where the wave is not displaced at all. So the blue dotted line, I drew it the same way as I drew the normal when we were analyzing refraction. So when you want to analyze just the oscillation of a wave, up and down, then displacement is up and down. And in this case, when they want you to measure the wavelength, you know that the x-axis must be, along this way, its distance. Is how does the displacement vary according to along the distance. So they normally it will be in meters, just the same here. That would be the official scientific unit, but because it's a small disturbance, it can also be in centimeters. So both of these readings are in centimeters. Okay? So the y-axis is displacement, and the x-axis in this case is distance, and the dotted line in the middle is the point of zero displacement or equilibrium point. Okay, so the amplitude will be the maximum height of the wave from there to there. So this would be the amplitude. Okay, so you would label it on the dotted line as a capital A. Okay, and measure it in centimeters with a ruler. And of course, if you don't measure it accurately, you may not get the 1 mark. Okay, so I haven't done that. You can have a look at the mark scheme. And then the wavelength is from two waves, the distance between two waves. So you draw it from here, the peak, to this point, the peak, and then hopefully that's the wavelength. So when you're drawing the wavelength, make sure you're drawing it from the peak to the peak of the wave, okay? And then again, if you don't measure it accurately, you may not get the 1 mark, okay? So basically, this is very easy if you don't know them. It's just very easy marks lost. So you do need to make sure you've got all of the key terms understood, and that's what your job is before the spring break is over. Make sure you've got all of your definitions from the syllabus understood. Okay, that's just knowledge. That's just what I call donkey work. You've got to do the hard work if you want to get a good grade. There's no other way to do it. Okay, so the next question says microwaves are part of the electromagnetic spectrum. So we did light waves before, which are also part of the electromagnetic spectrum, and microwaves are a bit like radio waves, yeah, and you use them in microwave ovens, although I don't tend to use microwave ovens. I don't think it's good for the food. Name the part of the spectrum, the electromagnetic spectrum, that has a lower frequency than microwaves. In other words, you need to know the electromagnetic spectrum. You need to know the electromagnetic spectrum and the order that the different family of waves come in. And the only one which has a lower frequency than microwaves are radio waves. Okay, so they have the lowest frequency or the longest wavelengths. Okay, it then goes on to explain microwaves travel at the speed of light, 3 times 10 to the 8 meters per second in air or in a vacuum. And a typical microwave has a wavelength of 2.7 centimeters. Calculate the frequency of this microwave. Now, if they're giving it to you meters per second and then centimeters, you have to change the centimeters into meters before you use the wave equation. Okay? So the wave equation is frequency times wavelength is the speed, but you want to work out the frequency, so you've got to do speed divided by wavelength. And if you put the numbers into this equation correctly, you'll get 1 mark. If you forget to change the power from centimeters, power of 10 is called. If you get it out by, say, a power of 2 because you forgot to change from centimeters to meters, I think they'll still give you 2 marks, but they will give you what's called a power of 10 error, that the student forgot to change the prefix here, centimeters, into meters. That's a silly mark to lose if you've practiced all of your prefixes, so you need to know them. And then the answer in frequency to 3 significant figures is 1.11, but you'd really need to round it up to 2 significant figures because the data provided is only known to 2 significant figures. You'll see this is known to 2 significant figures, and the speed of light is given only to 2 significant figures. So that means the data is only known to two significant figures. Okay, so that's another part of this question done. It now goes into an investigation. So a lot of investigation work is the process of science, and they expect you to know the scientific methodology. Okay, so this is very important that you learn it from year 7 onwards and even in primary school. A student uses a microwave source and a receiver to investigate microwaves. So the scientific method is to do with investigation work. So if you're investigating, you've got to do it scientifically. Photograph 1 shows how the student sets up their apparatus with the microwaves. So here's the microwave source. Here's a receiver which picks up the microwaves and converts them into electricity. And here you got what's called a non-digital meter, known as an analog meter. Okay? So the meter shows the strength of the microwaves detected because it's connected to the receiver. And the receiver changes it to electricity. Okay, a bit like a microphone can be used with an oscilloscope to show the sound wave as an electrical signal, the strength of the signal. So we don't really care about the units. The strength of the microwaves is measured in arbitrary units. For those of you studying in English where it's not your first language, it just means we don't really care about the units. The units are unimportant in this question. Just call them units, okay? The student varies the distance between the microwave source and the receiver, okay? And you can see they've got a ruler to see how far is the receiver from the mouth or the center. I don't know whether they're doing a measure from here or they're going to measure it from there. Okay, that's an important thing. So the distance can be varied, and that would be called the independent variable because it's the thing that you're deciding to investigate. And then they record the corresponding meter readings, which is the strength that the receiver picks up. Okay, so there it is. And then photograph 2 shows the meter reading for one of them. And you can see it's less than 70 and by one digit, and there's how many lines between 60 and 70. So they want to see that you can read a digital meter, and you can see it's 68. So the meter reading will depend on the distance, so it's called the dependent variable. Okay? So that's what your investigation. Remember, they don't care about the units, they just put the arbitrary units there. Arbitrary means irrelevant what the exact units are. And if you read it correctly, and remember in the exam you've got to write in black. So I'm writing in black, but I'm doing it with a highlighter pen. Okay. So here you would write 68 units. Okay. It probably is microamps or milliamps. Okay. So that's what it could be, and that's how you get the 1 mark, by making sure you've read the scale accurately. Okay. The next part is that they put the data into a graph. Okay, the graph shows the results of the student's investigation. Remember, the distance is the independent variable. In this case, they've used a standard method to put the distance on the horizontal axis and then the meter readings, yes, on the y-axis, so they're the dependent variables. The student concludes that the meter reading is inversely proportional to the distance, okay, obviously between the microwave source and the receiver. Now, inversely proportional actually means if you double the distance, the meter reading will halve. Okay, so inversely means whatever you do to one, the opposite happens to the other variable. Okay. Now, so they're telling you, in other words, to be inversely proportional, if you multiply the y-axis by the x-axis, the meter reading by the distance, it should give you a constant value. If it doesn't, it may look like it's inversely proportional, yeah, but it won't be. So you've got to do it mathematically. So I've circled 2 points, one in red and one in green. one in red I put here. I wanted to look at the 80 value on the y-axis, and then I wanted to look at the 40 value on the other axis, because I thought these two are far apart and we can easily see the green value on the y-axis here and the red value on the x-axis here. So the corresponding ones I've circled now in green and red. So you've got to use those values from the graph. Yeah? You should use the data from the graph to get your answer here. Yeah? They want you to simply see if you agree with the student's conclusion. So the way they've written it is comment on the student's conclusion. Use the data to work out your answer. So that's what you've got to do. So use the two values that I've shown you from the graph, the one in red and the one in green, multiply them together and you'll get 2 marks. Okay? You'll get 2 marks from doing this calculation. Then, so you calculated these two values. Then you compare your answers and you'll get another mark. So you've got to compare the answers and say they're not the same. If you multiply 80 by 12, is now about 960 arbitrary units. And then over here, 6 times 40 is 200. 6 times 40 is 240. Yeah, have I got it right? So they're nowhere near the same. They're not equal. So you've got to compare these answers and say they're not equal. So therefore, was the student's conclusion correct? That's what you want to comment on. So you say, according to the data from the graph, when you multiply the corresponding points, they do not give you an equal value. So just because it's curved downwards doesn't mean it's inversely proportional. Inversely proportional is a mathematical relationship. If you double one axis, the other one will halve. Okay, it's the opposite of directly proportional. And that takes us through both the waves questions, 11 marks here, and I can't remember how many marks were on the other one. So that's another part of this exam paper run through. If you found that useful, don't forget to like it, share it, and so more people get to watch the video. And if I get enough people watching these GCSE videos, I'll also upload the 2024 papers as soon as I've used them with my students. Okay, so if you want the more videos like this, you need to leave a comment and you need to show that there's enough students who are using the service. Thanks for watching. Catch you in the next video. Bye.